In the first trillionth of a second of its existence, the universe was a cauldron of unimaginable energy, a particle soup hotter than a quadrillion suns. Today, that energy has cooled and condensed into at least 2 trillion galaxies, each a spinning city of 100 billion stars. Our own Milky Way contains 400 billion suns, and the observable universe holds an estimated 10 to the power of 80 protons. The sheer overwhelming of reality seems undeniable. And yet, one of the most elegant and profound ideas in modern cosmology, supported by our best observational data, whispers a secret that defies all intuition. The total energy of the entire universe might be, with mathematical precision, zero. This isn't an approximation or a near miss. It is the proposal that everything, every star, every black hole, every particle of light, every conscious thought, is one half of a cosmic equation whose grand total is nothing. This isn't a near zero, but an exact, breathtaking balance. It's a universe running on a perfectly balanced set of books, a cosmic IOU written against the void. To grasp this, we must first redefine what we mean by energy. Our minds immediately leap to the positive, kinetic, and tangible. We think of the energy of motion, the thermal energy of a star, and, most famously, the energy locked within mass itself, as described by Einstein's iconic E is equal to mc squared. This is the positive side of the ledger. All the matter, all the antimatter, all the photons, neutrinos, and dark matter particles contribute to a colossal positive energy budget. If you were to add it all up, the number would be staggeringly large, a testament to the universe's immense scale and density. But this is only half the story. The other side of the ledger is occupied by a more subtle, yet equally powerful entity, negative energy. In cosmology, this primarily takes the form of gravitational potential energy. Think of it this way. To pull a satellite away from Earth's gravitational pull, you have to expend energy. That energy is stored in the gravitational field between them. Conversely, if the satellite falls back to Earth, it releases that energy as heat and motion. Because you have to add energy to separate objects, gravity is considered a binding force with negative potential energy. Every star, every galaxy, every cluster of galaxies is a well of negative gravitational energy. The more tightly bound a system is, the more negative its energy. The zero-energy universe hypothesis, an idea first tentatively explored by physicists like Pascual Jordan in the early 20th century, posits that these two sides are perfectly matched. For every joule of positive energy created in the form of a particle, an equal amount of negative gravitational energy was simultaneously generated in the fabric of space-time. A popular analogy is digging a hole on a flat piece of ground. You create a mound of dirt, that's your positive mass energy. But you have also unavoidably created a hole of equal volume. That's your negative gravitational energy. The net change in the amount of dirt on the flat plane is zero. Our universe in this view is the result of a monumental act of cosmic excavation. This concept carries a staggering implication, one that cuts to the very heart of theological and philosophical questions about creation. If the universe's net energy is zero, it could have arisen from nothing without violating one of the most sacred laws of physics, the conservation of energy. A universe from nothing is often dismissed as magical thinking, but in a zero-energy model, it becomes a possibility rooted in physics. It doesn't require a prime mover or an external source of infinite energy to get started. It simply requires a mechanism that allows for the spontaneous separation of positive and negative energy from a state of perfect nothingness. How can such an extravagant reality, teeming with complexity and consciousness, fundamentally be a debt owed to the void? What physical process could possibly orchestrate this cosmic accounting, creating a universe from a cosmic loophole? From that paradox of perfect balance emerges a mechanism of impossible speed and scale, a theory that not only explains a zero-energy universe could come to be, but also solves some of the deepest puzzles of the standard Big Bang model. This is the theory of cosmic inflation. Before its development in the late 1970s and early 80s, cosmology faced crippling problems. One was the flatness problem. Observations from missions like NASA's Wilkinson Microwave Anisotropy Probe and later the European Space Agency's Planck satellite have confirmed that the geometry of our universe is astonishingly, almost perfectly flat. Any significant curvature, positive or negative, in the early universe would have been magnified over 13.8 billion years, causing it to either collapse back on itself in a big crunch or expand so rapidly that galaxies could never form. For our universe to be as flat as it is today, its initial state had to be fine-tuned to an accuracy of 1 part in 10 to the power of 62, a precision akin to firing a bullet across the cosmos and hitting a single atom. The standard Big Bang theory offered no explanation for this miraculous fine-tuning. Building on that cosmic balance, the prevailing theory of inflationary cosmology offers a mechanism for this impossible feat. The breakthrough came from physicists like Alan Guth and Andre Linde. They proposed that the Big Bang wasn't the beginning, but rather the end of a far more violent and exotic epoch. In the first sliver of a second, from roughly 10 to the negative 36 to 10 to the negative 32 seconds after the beginning, the universe underwent a period of hyper-accelerated, exponential expansion, driven by the energy of a hypothetical quantum field called the inflaton field. This field permeated all of space, and like a ball perched precariously at the top of a hill, it was in a high-energy false vacuum state. The energy locked in this false vacuum had a remarkable property. It exhibited negative pressure, acting as a powerful anti-gravitational force that drove space to expand faster than the speed of light. During this brief inflationary epoch, a patch of space smaller than a proton was stretched to a size larger than the entire observable universe today. This incredible stretching ironed out any initial curvature, just as inflating a crumpled balloon smooths out its wrinkles. This solves the flatness problem naturally, without any need for exquisite fine-tuning. But where did the energy to start this process come from? This is where the zero-sum game comes into play. The engine of inflation is a loan, borrowed directly from the quantum void. The Heisenberg uncertainty principle states that one cannot know both the energy and the time duration of a particle or system with perfect accuracy. A consequence of this, expressed as delta E delta T greater than or equal to h bar over 2, is that the law of energy conservation can be briefly violated. Nature allows for the spontaneous creation of virtual particles that pop into and out of existence, borrowing a tiny amount of energy from the vacuum for a fleeting moment before vanishing. Inflation theory suggests the universe itself began as such a fluctuation. This isn't some arbitrary borrowing, it's a quantum event that, under the right conditions, could become runaway. The borrowed energy kicked the inflaton field into its high-energy state, and the expansion began. As space-time stretched, the negative energy of the growing gravitational field perfectly counterbalanced the immense positive energy of the inflaton field. The loan was paid back in real time. When inflation finally ended, the inflaton field decayed, releasing its energy and flooding the universe with the hot, dense soup of particles that we call the Big Bang. The universe was left with a vast amount of matter and radiation, a flat geometry, and a net energy of zero. The evidence for this is etched into the oldest light in the cosmos, the cosmic microwave background. The temperature of this light is uniform to 1 part in 100,000 across the entire sky, solving the horizon problem. Furthermore, the tiny quantum fluctuations that existed during inflation were stretched to astrophysical scales, becoming the seeds of cosmic structure, the very density variations that allowed galaxies and clusters to form. The Planck satellite mapped these variations with stunning precision, and they matched the predictions of inflation perfectly. Our entire reality appears to be a magnificent, self-sustaining illusion, a fleeting manifestation of a quantum loan that never truly needed repayment. What does this profound debt imply for the universe's ultimate fate and our place within its grand zero-sum equation? This vision of a self-creating zero-sum cosmos hinges on one elusive concept: negative energy. It's not just a clever accounting trick, it is a physical, tangible feature of space-time itself. To truly understand it, we must move beyond simple analogies and into the heart of Einstein's theory of general relativity. Here, gravity is not a force pulling objects together, but a consequence of the curvature of space-time. Mass and energy tell space-time how to bend, and that bending, in turn, tells matter how to move. The source of this curvature is described by a mathematical object called the stress-energy tensor. It's the universe's rulebook for gravity, and it contains more than just mass. It includes pressure, momentum, and shear stress. For the familiar matter around us, this tensor dictates that positive energy density creates an attractive gravitational field, the kind that holds planets in orbit and galaxies together. This warped geometry, this gravitational well, is where the negative potential energy is stored. It is as real as the mass that creates it. It is the ghost in the machine of the cosmos. For decades, negative energy in this gravitational context was the primary candidate for balancing the universe's books. But in 1998, cosmology was turned on its head. Two independent teams of astronomers studying distant supernovae discovered that the expansion of the universe is not slowing down as expected, it is accelerating. Something is actively pushing space-time apart, overpowering the collective gravity of all the matter within it. This mysterious entity was named dark energy, and it now appears to make up nearly 70% of the energy density of the universe. The most fascinating aspect of dark energy is that, according to general relativity, to cause cosmic acceleration, it must possess a strong negative pressure. It is, in effect, a real, measured, and dominant form of energy in our cosmos that behaves in a profoundly negative way. This discovery, confirmed by countless subsequent observations from sources like the Hubble Space Telescope and the Dark Energy Survey, adds a massive new term to the negative side of the cosmic ledger. The universe isn't just balanced by the negative potential energy of gravity, it is dominated by a pervasive field whose very nature is repulsive. This brings us to one of the greatest unresolved mysteries in all of science, the cosmological constant problem, or the vacuum energy problem. Quantum field theory predicts that even empty space, the vacuum, should be teeming with virtual particles, giving it an intrinsic energy. When physicists try to calculate the theoretical density of this vacuum energy, the result is absurdly large, about 10 to the power of 120 times greater than the value we actually observe for dark energy. This is, by far, the worst theoretical prediction in the history of physics. However, the zero-energy universe hypothesis offers a tantalizing, if speculative, perspective. What if the natural state of the universe, the true vacuum, has precisely zero energy? What if the immense positive energy of quantum fluctuations is perfectly canceled by an equally immense negative energy from some yet unknown physical law? In this picture, the tiny positive value of dark energy we observe today isn't the total. It's just a small residual imperfection, a slight imbalance in a system that is otherwise perfectly canceled out. This balanced equation would be the ultimate law. If this is true, it recasts our entire existence. Our universe is not a foundational reality, but an emergent one, a complex phase transition of nothingness, like a snowflake is an intricate structured phase of simple water vapor. All the complexity, all the beauty, all the consciousness that has arisen within this cosmos is an artifact of a temporary separation of positive and negative, a magnificent but fleeting asymmetry in a fundamentally symmetric and null state. The universe doesn't need a reason to exist. It exists because nothing is an unstable state. In the grand cosmic silence, the potential for everything and its opposite was always present. a balanced equation waiting to be written in stars and galaxies. And we, a temporary clause in that magnificent self-canceling sentence, are here to read it.